So finally now, we can move to the next topic in the course, which is the theory, the formal theory, actually now, of atoms. And what's really fun about this is that it takes the course now back full circle. Because we began, if you will recall, by assuming the existence of atoms and trying to understand their properties from first principles, following this dream that Empedocles had of going back to the basic ingredients of matter and considering their interactions. And now we have all the tools we need to actually carry out that program. So let's think about what goes into a typical atom. Our key ingredients in nature, we had decided and have been studying from the beginning of the course, are the nucleus, which I'll draw as a larger dot because it's much more massive, and the electron. So we're going to have here a nucleus and the electron, which I'll just abbreviate as E minus, and the electron will have mass lowercase m and a charge lowercase q, which we know is exactly minus the charge on the electron. The nucleus itself will have a much larger mass, which I will call capital M, which is much greater than lowercase m, and it will have a charge, which I will call capital Q, which in general is some integer number of proton charges, so it's positive. That integer number is known as the atomic number. We can call that Z, times then the fundamental unit of charge, E. Finally, we need to know what the potential is so we can build up the Hamiltonian, and the interaction between these, as we had said at the very beginning of the course, is just this, love and strife from Empedocles, namely the attraction and repulsion that is built into the Coulomb interaction. So there's also going to be this Coulomb potential that describes the interaction. And the Coulomb interaction is just Coulomb's constant times the product of the charges, Q times Q, divided by the distance between them. So I will call this distance r. And this then is the problem whose Hamiltonian we are going to write down, and then with it we will solve the time-independent Schrodinger equation. The time-dependent Schrodinger equation. Independent Schrodinger equation, say, to get the energy levels of this atom. Now, there are a number of tricky aspects to this problem that we are not quite yet used to. Namely, first, typical atoms will actually have more than one electron. We've only thought right now about what happens when we have one quantum particle. We're not ready yet to think about multiple quantum particles. That will occur in the next course. That's called in your next course on quantum mechanics. So we're going to put that aside. But nonetheless, we can think about other types of atoms with heavier nuclei that have larger charges. For example, we could consider a helium atom where Z equals 2, but which only has one electron in it. That would actually be technically the helium ion, right? Or we could go up next to lithium and look at the lithium double plus ion. So there's a whole series of ionized atoms that we can consider that actually have just one electron in them but have different charges on their nuclei. Those are called the hydrogenic type atoms, and those will be the ones that we will actually focus on. The reason why we're not going to go at the moment into what happens when we have multiple electrons is because we have another complication here, because not only do we have multiple electrons, but the atom actually exists in multiple dimensions, namely in 3 dimensions. So far we've only really looked at one-dimensional problems, so we will have enough on our hands just thinking about 3 dimensions. So let's begin our thought process on how we would do a quantum system of this quantum treatment of this system in 3 dimensions. So we want to note that D equals 3 dimensions. Fortunately, right? We've been educating ourselves very well here, so I think we are very much up to the challenge to very quickly figuring out what our quantum representations are going to look like in 3 dimensions. So in 3 dimensions, the representation of our quantum state, and we will do this in the position representation at first. The position representation will then be some wave function, which is now a function of all 3 coordinates, x, y, and z, so that we are able to determine the probability density for finding the particle at any particular location simply by taking this complex wave function and squaring it. So I think that's a pretty straightforward generalization. The next thing, of course, that we need once we have a representation is access to the corresponding operators. Now, these operators in this position representation, there's more of them now. We have not only an operator that gives us the average value of the x-coordinate, we also need an operator for the average value of the y-coordinate and for the z-coordinate. And also, we're going to need these for the momenta. And there's a momentum in the x direction, a momentum in the y direction, and a momentum in the z direction. For these operators, the location operators, because we are in the position representation, those I think are pretty clearly going to turn out to be just what you would multiply this probability by to calculate their averages. So that's clearly going to be just x, y, and z, the values of the corresponding coordinates. For the momenta, that's going to take a little bit of thinking. But we can pretty much guess what they're going to be, and it will actually follow from the following fact from the de Broglie hypothesis. So de Broglie is going to teach us, if we are in multiple dimensions, that if I have a pure state of momentum p, and p has 3 components, it's actually a vector. And the way we connect momenta to waves, right, or the way we write down waves is, of course, with a wave vector. The conversion constant is going to be Planck's constant, which will ensure that the wavelength here associated with these waves is just lambda is just h over the magnitude of p. And by making k in the same direction as p, we ensure that wave packets would be traveling in the same direction in which the momentum of the particle points. So all of that lines up nicely. But to make such a pure state, right, a pure state of that momentum is going to be just proportional to then the corresponding wave, e to the I k dot x. Or I guess I would rather write this as k dot r, where we are saying that r actually is the vector that has all of these coordinates, x I hat plus y j hat plus z times k hat. Now, as soon as we have this, we realize if I want to pick out a particular component of momentum, I should just take the derivative with respect to the corresponding variable that multiplies it in this dot product. So to get the x momentum, there would be the factor of h bar to turn it into a momentum divided by I times the x derivative, and that x derivative is what will pull out the kx for me. And I will likewise have the same combinations for the y momentum. I take the y derivative to pull out k sub y from the dot product, and for pz, it's h bar on I d by dz. So that shows us how we would quantize any problem in 3 dimensions. For the atom, then, we can write down finally the Schrodinger equation, which we will need to solve. For the atom, we first always begin, for any system, we write down the Hamiltonian, which is now p squared over 2m, right? That's the kinetic energy. One comment I really want to make on this problem, which I should have made a little bit earlier. My nucleus, notice, here I'm going to put a little line here so we don't get confused. The nucleus is very heavy, right? So actually, Because it has a much larger mass, much like the sun at the center of the solar system, when we analyze the orbits of the planets, we really ignore the fact that the sun is moving also. You may recall that, strictly speaking, there's some point here, which is the center of mass of the system, about which in this case both particles are moving. But because this is so massive, the center of mass is essentially at the same location as the nucleus, and there are only very small corrections that occur. So to a very good approximation, because the nucleus is very heavy, we can treat it as essentially stationary. And I'm going to put it at the origin of this, and we're going to use it for the origin of our coordinate system. So that's just a little technical detail. Why I bring that up is that the Hamiltonian should be the total kinetic energy plus the total potential energy. And in this case, that would be a kinetic energy of the kinetic energy is the kinetic energy of the nucleus plus the kinetic energy of the electron, right? But the kinetic energy of the nucleus, as we've said, we can approximate as 0 to a very good approximation. So I'll then just have the kinetic energy of the electron. The particular potential that we're talking about, there's only one interaction. It's this Coulomb interaction here that I had written down. And now we can be a little more explicit about what these terms are. The kinetic energy of the electron is its momentum squared divided by twice its mass. But notice I'm writing this down in somewhat of a funny way. And what's funny about this is, remember that the momentum now is a vector with 3 components. So the total kinetic energy is the total momentum squared. The magnitude of that vector squared is the sum of the squares of the individual components. For the Coulomb interaction, I can now write this down directly also. The Coulomb interaction is Coulomb's constant times the product of my charges. So that's Coulomb's constant times ZE times minus E. So there's a net minus sign. I then had a factor of Z. I had Coulomb's constant times, I had ZE times E, so there's actually an E squared. And then it's just 1 divided by, then, the distance between the nucleus and the electron. Now the nucleus, again, we are going to take as the origin of our coordinate system. The electron is sitting at location X, Y, and Z. So that radius is actually the square root of X squared plus Y squared plus Z squared. That's my Hamiltonian. So then I can write down finally, and we can then conclude the lecture, the time-independent Schrodinger equation, which will then take the following form, right? When I insert each of these momenta, I get a minus sign from squaring the i's, and a minus h bar squared divided by 2m in all cases. So there's going to be minus h bar squared divided by twice the mass. And that multiplies, the first term gives me the x derivative squared. The second term gives me the y derivative squared. And the third term will give me the z derivative squared. And all of this is applied to my wave function. And I'm going to call that bound state wave function a capital psi. I won't be using capital phi anymore for that because I need capital phi for other things. I'm going to be running a little bit out of Greek letters. Then, of course, we have the potential piece of the operator. That's going to be multiplying my wave function, kce squared, right? 1 over, I'm really copying this down over again for the potential piece at least, x squared plus y squared plus z squared. That's all multiplying my psi of x, y, z. And all of what I've written so far is, of course, just the Hamiltonian operator applied to my wave function. But to be the time-independent Schrodinger equation, I'm just saying this is a pure state. So this will be multiplying just the energy times then my original wave function back again. So what we need to do now is to develop special techniques that will help us address all of these additional complications that are coming in now due to the fact that we are living in 3 dimensions, and that's what will be the next topic that we take up.